This is the well-known periodic table with its 118 elements, which we can think of as the bricks used to construct our universe. Everything we know, from smartphones to our computers, to the distant planets, stars and galaxies, is composed of these elements. The latest element was discovered not so long ago, just in 2002. But is it the last? This is a very debatable question, as my research showed. Nonetheless, the first element is very clear: hydrogen. And if it is the first on a periodic table, does it mean it is the first to be created? Could we possibly find the very first of 180 known elements that was created nearly 13.8 billion years ago? Sounds impossible, right? But we're going to try with a little help of physics, chemistry, and a dash of cosmic curiosity. Make yourself comfortable as we begin our journey. Have you ever wondered why the flame from a lighter burns with a different hue than the blue gas flame of a stove? Or why a match lights up with a warm yellow-orange glow, but fireworks explode into a dazzling display of greens, reds, and blues? All these colors come from different chemical elements burning, each adding its unique touch to a fairy rainbow. By understanding a bit of physics, we can decipher the elements involved just by looking at the color they produce. Let's use a prism, just like the one from the Pink Floyd album cover. When the light from a flame passes through the prism, it separates into a spectrum, revealing component colors much like a barcode. This special barcode is unique to each element and tells us precisely which element is present in the flame. It all boils down to the structure of atom and their electrons. Hydrogen atom. A single electron orbits around the nucleus. When the electron gains energy, whether from heat or light, it gets excited and jumps to higher orbit. But it can't stay there forever, as the law of conservation of energy states energy can neither be created nor destroyed, only converted from one form to another. So it eventually falls back to its original orbit, releasing energy in form of light. The color of light depends on the amount of energy released. A small amount might produce red. More energy gives off green, and a lot of energy might result in blue or violet. Now let's apply this knowledge to a larger scale. Say the sun. If we pass sunlight through a prism, we see a continuous spectrum of colors, like a smooth rainbow. But when we analyze this spectrum with modern equipment, we notice it's actually full of dark lines, gaps where certain colors are missing. These lines are called absorption lines, and they occur because certain elements in the sun's outer layer absorb specific wavelengths of light from the core, leaving dark gaps in the spectrum. By studying these absorption lines, scientists realized that the sun, and indeed all stars, are not burning good or coal as we once thought, but are undergoing much more complex nuclear reactions. In fact, the elements found in the sun are the same as those on Earth, plus a few more that were discovered in the spectra of the stars. Helium, for instance, was first identified in the sun's spectrum during a solar eclipse in 1868 and was later found on Earth. But to find the first atom, we need to travel back in time to the very birth of the universe itself. Let's set the stage. About 13.8 billion years ago, the universe was born in a cataclysmic event known as the Big Bang. But contrary to popular belief, the Big Bang wasn't an explosion in space, it was the expansion of space itself. It was the moment when everything that exists today was compressed into a single, infinitesimally small point. Then, silent boom, as there was no sound, space began to stretch and expand. And so did the fabric of reality. In fact, the first 10 to the negative 43rd second after the Big Bang, a time so short that we don't even have a proper word for it, the universe expanded exponentially, faster than the speed of light. This period is known as cosmic inflation, and it set the stage for everything that would come after. As the universe expanded, it also cooled. Conditions became just right to give rise to the building blocks of matter, the quarks and electrons of which we all are made. A few millionths of a second later, quarks aggregated to produce protons and neutrons. Within minutes, these protons and neutrons combined into nuclei. As the universe continued to expand and cool, things began to happen more slowly. It took 380,000 years for electrons to be trapped in orbits around nuclei, forming the first atoms. These were mainly hydrogen and helium, which are still by far the most abundant elements in the universe. So hydrogen, the very first element, was born out of the chaos of the Big Bang, with just one proton and one electron. It is the simplest element in the universe. Hydrogen may be simple, but it's far from boring. Hydrogen atoms began to cluster together under the influence of gravity, forming massive clouds. And around 150–200 million years after the Big Bang, these clouds became denser and hotter until eventually they ignited, giving birth to very first stars. Stars are the universe's power plants, forging elements in their cores through the process of nuclear fusion. When the first stars formed, they were mostly composed of hydrogen and helium. However, under the immense pressure and temperature in their cores, these elements began to fuse together, creating new, heavier elements. This fusion releases an immense amount of energy, enough to power a star and produce the heat and light that makes life possible on Earth. In the cores of these first stars, hydrogen atoms were squeezed together to form helium. Once a star has converted all its hydrogen into helium, it starts fusing helium into even heavier elements, such as carbon and oxygen. The universe's first stars were massive, often more than 10 times the size of our Sun. They also had shorter lives than stars today. As they lived, they burned hydrogen and produced the elements up to the iron in the periodic table. Once a star gets to fusing iron, it is doomed. This is because fusion of iron takes more energy than it produces. But here's the catch. Not all stars are capable of creating all elements. Smaller stars, like our Sun, will eventually run out of fuel and cool down, turning into a white dwarf. But the real fireworks happen with massive stars. Those at least 8 times the mass of our Sun. When a massive star runs out of fuel, it can no longer hold up against its own gravity. The star collapses, and in a fraction of a second, the core implodes, leading to one of the most spectacular events in the universe, birth of a supernova. During this explosion, the temperatures and pressures are so extreme that elements heavier than iron can form. A supernova can release more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifetime. The supernovae are responsible for scattering the heavy elements across the universe. Gold, platinum, uranium, all these elements heavier than iron, were forged in the heart of dying stars and spread out into space. So the iron in your blood, the calcium in your bones, and even the gold in your jewelry come from remnants of an ancient supernovae. But if you thought the story ended with supernovae, think again. In some cases, the remnants of a supernova don't just scatter elements, they collapse further into even denser objects, like neutron stars or black holes. Neutron stars are incredibly dense, with the mass of the Sun packed into a sphere just a few kilometers wide. They are so dense that a sugar cube-sized amount of neutron star material would weigh about 1 billion tons on Earth. And when 2 neutron stars collide, oh boy, the universe puts on one of the most dramatic shows. The collision creates gravitational waves, gamma rays bursts, and even more elements. It's estimated that a single neutron star collision could produce as much gold as the mass of 10 Earths. After a supernova explodes, the remnants of the star are scattered into space, mixing with interstellar medium, basically the gas and dust that floats around the vast space between stars. Over time, gravity pulls this material together to form new stars and planets. These regions, known as the stellar nurseries, the most beautiful thing that we have ever observed, are where the next generation of stars is born. Inside these stellar nurseries, dust and gas clamp together, forming new stars. Around these young stars, disks of gas and dust can coalesce to form planets, moons, and other objects. This means that every planet, including Earth, was formed from the remnants of previous stars. Quite literally, we are made of stardust. The very atoms that make your body were once part of a star, so next time if someone tells you to reach for the stars, remember, you're already there. All these elements created by stars, carbon, oxygen, nitrogen, phosphorus, sulfur, are the building blocks of life as we know it. They combine to form the molecules that make up everything from DNA to proteins to the very cells in your body. This cosmic chain of creation spans billions of years, from the first hydrogen atoms formed after the Big Bang to the complex molecules that make up living organisms today. The human body is made up of about 7 octillion atoms. If you tried to count all the atoms in a human body, counting an atom per second would take you longer than the current age of universe. But we cannot stop here. The periodic table expands beyond the elements we know, hinting for more mysteries. The elements heavier than uranium are not naturally occurring on Earth and have to be created artificially in laboratories or during supernovae or neutron star collisions. The Earth's uranium had been thought to be produced in one or more supernovae over 6 billion years ago. More recent research suggests some uranium was formed in the merger of 2 neutron stars. When stars merge, they create gravitational waves and unleash a torrent of heavy elements into space, enriching future star systems with the building blocks needed for planets and perhaps even life. Every day, astronomers, physicists, and chemists are working to better understand the cosmic processes that shape our universe. From studying distant galaxies and black holes to unrevealing the mystery of dark matter and dark energy, we're always pushing the boundaries of what we know. Scientists observe that everything in the universe, from humans to planets, is composed of matter, which is defined as any substance that has mass and occupies space. While matter is everywhere in our daily lives, it comprises less than 5% of the total universe. 95% of the universe is made up of dark matter and dark energy. These are words that scientists have come up with to give name to the mysterious invisible side of the universe. Dark matter, similar to ordinary matter, has mass and occupies space. However, it doesn't reflect, absorb, or emit light in any way that we can currently detect. Scientists estimate that dark matter constitutes about 27% of the universe. 68% of the universe is dark energy, but scientists know even less about it than they do about dark matter. But something like dark energy must exist to explain the universe's accelerating expansion. As we look up at the stars, we're looking back in time, seeing the light that left those stars millions and even billions of years ago. Each star is a window into the past, a clue in the puzzle of our existence. From the first hydrogen atoms to the most complex molecules, the universe has been on a 13.8 billion year journey to create everything we see around us. Despite all we've learned, the creation of elements is still shrouded in mystery. Where does the periodic table end? How can we create elements even heavier than those found in nature? We've already synthesized elements up to atomic number 118, but these are highly unstable and exist only for a fraction of a second. But this second is a whole life for a scientist. So remember that you're part of a story that began billions of years ago, written in the stars. And if universe can create something as complex and beautiful as you from few simple elements, imagine what else is possible. If you enjoyed this video, don't forget to like and subscribe. Thank you for your time. See you in the next one.